Just a reminder, tonight is the blockchain, Bitcoin, blah, blah, blah talk at the Grace meeting. It's at 7 p.m. in the terrace room, correct? Oh, yeah. I got the whole thing. I got pictures. Pic- Oh, this is a minimum of 4 hours. It's not more than an hour. Oh, but if we have to be out of there by 9, that means I have 2 hours.
Yeah, but like people really start coming in and set up at 8. So like
Yeah, see, now you're backpedaling. I hear
they
it.
only reserved it for 7 to 8.
It'll be less than an hour. Okay. So I encourage you to come to that tonight or tell your friends about it or whatever so we have a good showing. It sounds like we're having pizza and stuff there. All right. So we were talking about, we were finishing up our server stuff. Okay. So this is where we start listening to port 8080. Last time we talked about IPv4 versus IPv6 for IP addresses, that kind of stuff. We will test something here in a few minutes just to see how campus works. Actually, Corey, do you happen to know, like if I have an IP address on this machine, so this guy's going to give me, if I do ifconfig, I get my IP address, which is the 172, whatever. So this is a routable IP address, technically. If I'm off campus, can I hit that IP address, or does it block me on the way back in? Okay, because we saw last time that we can hit it, but we're still on campus. So when I say try to telnet to that address, it's leaving my laptop, going through, hitting our edge router, but never actually leaving campus. It's still pinging around inside of our network, which is why I was able to get back to it. I can, I'm sure that's probably the case. We could always remote into one of my machines at home and telnet back in and, or at least ping it and see if it's alive. But I think it probably isn't. So punchline there is that you wouldn't necessarily be able to run a web server off of this on campus because campus is blocking your traffic back. But AWS would, not prevent you from doing this. Okay, so this guy right here, this accept, is a function that blocks. All right, so this function sits there and it uses the server we've set up, right? So that's the server file descriptor. It also, we pass in the address of this socket address. So that's for it to give us information about the guy that was just connected. And then we also pass in the length of that socket address. So this is us sitting here by the phone waiting for it to ring. And this blocks. So we will not get to the next line of code until somebody actually connects. All right, so if we run this, this is called server.c, right? And I do that. Right now, it is sitting on that line right there at 52, waiting for there to be an incoming connection. Okay? And then if I open up this and I say 127.0.0.1, where's my, is this it? Oh, 8080, it's right. It didn't hit on there. So let me, and that's because the 127.0.0.1 is the home address of this machine, and this machine is a different machine. For some reason, I thought it was mapping locally. So I'll give it the full IP. And like we just said a second ago, this is going to leave my laptop but stay inside of the campus network. Right, so this guy's trying to connect. It's they're not speaking HTTP at this point. If I go back to this, is he connecting? It should be hitting that server. Oh, it doesn't give us actually a message that it was connected because it's waiting for a read. So if I just do a quick printf connected, we'll go back in here, I'll compile and run it again. And then we'll come up here. Not sure why I opened a new. Oh, it's not connecting through port 8080 there. It says it's trying to connect. So maybe it actually is blocking across networks. Well, that'll be unfortunate, but. Well, yeah, but I'm getting, I think the IP address, this is a Concordia IP address, so I think it's doing a local, it's like creating a local shell inside my web browser. But I'm not able to get back to it from the machine. I can telnet to it from, I wonder if Links is on here. No. Because if I do telnet, we could even do the full IP 8080 like that, and then I click back over here, it's recognized I'm connected. So I've spit out connected. So at that point in time, what it's done is this dude has now stopped blocking. We've accepted an incoming connection. It's been stored inside of new socket, and the information related to it's been filled into address. We didn't print out a failure here. We got to this line right here, so we're connected. Now it's waiting for me to read something in. So this is another blocking line. So this guy right here is trying to read up to 1,024 bits. That's on this one here. So if I type in LOL and I press enter, it's now going to print out whatever it read in there. And then it sends, so it'll print out locally over in this one. So it should print out LOL. That's what I sent. Then it's going to send over the socket. So to this is the new socket. This was the client that connected. It's going to send whatever's stored in my variable called hello, which is just the, was it some hello message, hello from server. So it's going to send to that socket this string, and here's the length of that string. And then let's look at the send. I want to see what that last thing is. I think that's the default protocol, right? Yeah, I think we looked at it last time. That's the TCP IP. So it's going to send this message that has this length using the standard internet protocol to that new socket. And that's when I received it over here. Here's the hello from server. That's the guy that I received. And then locally, the server's printing out hello message sent. Like this. Make sense? Okay. So let's see if there's a way I can mimic. Well, should be able to do this. Copy this. Doesn't know where to find read. That in socket? No, I think we saw last time that a couple of these things are actually going to be different on my local machine. All right, not the end of the world. So, in any case, this read function reads in from the socket. The send function writes out to the socket. So this is how this is our scanf. This is our printf equivalence. Okay. Now, effectively, we've now created a web server-like thing, with the exception that it's not actually serving web pages at this point. It's just taking some connection in and then spitting out a message back, so kind of proof of concept. Now, what if I wanted to allow more than one person to connect at once? Because right now, once one connection's come in, it's dead in the water, right? So if I just show that again here, I'll go ahead and I'll start my server again. Server's listening. I'll go ahead and connect here. And then I'm going to create a new terminal down here. And I'll go ahead and do, so notice here in our server, it says connected. So I'll tell that to, that didn't work nearly as well as I expected it to. We'll just do localhost since I don't remember the IP address. Port 8080. So we're trying to connect there, but notice that this guy hasn't received yet. So this dude's trying to connect. Actually, it says connected to localhost 8080. Well, this will actually be interesting. So let me type in LOL here. This guy sent the message. Yeah, we didn't get it on the other side. So he was able to connect on the port because we had bound to port 8080, but nobody was actually listening on the port. So he was kind of like next in line. It was a little bit misleading how he said he was connected. He wasn't actually connected to our server. He was connected to our port 8080, or in line for our port 8080. Now, what would be nice is for us to be able to accept multiple incoming connections. So that means that after we connect something here, we actually, maybe, well, let me ask you this. Based on what we've learned so far in here, how can I have more than one incoming connection? Okay, I could maybe just create a giant pool of sockets, but keep in mind that all these sends and reads, well, certainly the reads at least, are blocking, correct? So now we have 30 sockets that have been connected, but I'm still waiting to read from whoever's first in line before anything else happens. How else can I pull this off? Go ahead. We don't know about threads yet. We know about something like threads. What's the something that's like threads? We have to be careful when we talk about it that we make sure we enunciate mixed company. Fork system call. Okay, so the fork system call will allow us to fork a child process. So what we can do here is we can say, we'll just do some bad programming, I guess. Say while true. So this guy's just going to be an infinite listener. We will go ahead and try to have an incoming connection here. Now, when that incoming connection occurs, what are we going to do? Well, at this point, I know that I have a new connection. If I'm still kicking right here, we have a new socket that we've communicated with. So the fork system call, we've looked at fork already, right? We've actually done an example of it. We just talked about it. Okay. So let's look at, here, I think I can look at this on mine, and it's the same. So this guy creates a new process. It's in, let's make sure this is in our code. I don't remember if it is. This is a Unix standard library. All right, so I'll bring in the Unix standard library. All right, so this guy, the fork system call takes no parameters, but will return a process ID. All right, so depending on what it returns, we'll know who the child is. So let's just experiment with this. So I think the child will be a real process ID, where the so the child gets a 0, saying, "Look, you're new." The parent finds out who the child was. Okay, so fork will return a value of 0 to the child and returns the process ID of the child to the parent. So let's see this in action. So I'll go ahead and just for a moment, let me just comment this stuff out. Actually, we don't even need to worry about it. We're never going to get there. So I won't waste my time commenting it out because we're in an infinite loop here. It could be, infinite loop might actually be a little dangerous with the testing thing. So just for a moment, we will put it back in the infinite loop, but because I'm only partially testing this, let's just cut that for right now. All right, so after we've connected, I'm going to go ahead and I'm going to say, now it's a PID type, although we can store it in an int. So int PID is equal to fork. Then we'll ask if PID is equivalent to 0, printf, hi, I'm the child. Else, printf, I'm the parent. Something like that. All right, so we'll see the fork call. This guy will get called. It'll return a process ID. We'll say, am I the child? If the process ID was 0, then I'll print out on the child. Otherwise, I'll print on the parent. So both of those should print out. And they should be coming from 2 different processes. And actually, the parent can say, my new baby is named %D PID. Should give me the process ID of that guy. All right. So I think I was running the server here, right? Yep. So let's go ahead and compile this again. A.out. I'll go ahead and just connect. So here's the, I'm the parent. My new baby is named 4603. And then, hi, I'm the child, connected. So now if I, so now I have, there's 2 processes running, correct? Now, for the moment, both of those processes are doing the same thing. I have identical logic for them. But at this point, we have the process associated with this guy, and then this brand new child process, 4603. Okay? Now, let's go ahead, and for the 4603, I need to bring 4603 to the foreground. Oh, such job. We have to do a listing. Well, it's not overly important for right now. There we go. All right, so in any case, we have a parent and we have a child. Then we went on to the logic. Both are connected. I have the parent right here. Now the child is technically still waiting somewhere. I should be able to kill it. Kill 4603. But it's possible he didn't have a connected socket. So that's why it didn't show anything else there. Okay. So what I'm going to do now is I'm going to go back into our code. And what we want to do is we want to have the parent spin back around and listen for another incoming connection. We want to have the child do the logic associated with, dealing with this socket we just had connect. Okay? So we'll go ahead and fork. And I'm going to go ahead, I'm going to put this in our while loop here. All right, so while true, go ahead and get the incoming connection. Then we will fork. Then we'll say if we're the child, do this logic associated with the child. And what's the logic? We'll print out connected, blah, 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 return 0. All right, so that's what we do for the child. Exact same logic we had before. Else, we must be the parent. What should the parent do? We didn't actually need to throw this in the else because it would just naturally roll back up to the loop. So inside this infinite loop, we wait for a connection. When one comes in, we fork. If we're the child, we do the logic associated with that, and then ultimately end. That'll kill it. It'll get us out of the infinite loop, right? A return statement makes a function or makes the program immediately end. Otherwise, if we're not the child, we'll hit the end of the for loop, spin back up. Is true still true? Yep. It'll listen for another incoming connection. All right. So now what we should be able to do, get rid of this guy, is we now should have a server that can accept an infinite number of incoming connections. So we'll go ahead and we'll start our server up here. Oh, is it? It's not true in this language. It is. All right, so it's waiting for him. It's 1 because Booleans are implemented as 0s and 1s in this language. All right, so we're waiting for an incoming connection. So we're sitting here at this first accept. I'll go ahead and connect from this guy. So now we've had an incoming connection. If we really actually wanted to see this happen, let me just stop this real quick I'll go ahead and throw an else in here. So we printed out to the child connected. Let's go ahead and do an else here. And we'll say printf created child we'll do \n here. And then what I'm going to do is I'm going to do a printf right up here that just says listening. That way we'll know when it starts listening a second time. Okay. So let's start. Let's compile it and run it again. All right. So now it's listening. So how do you spell listening? Is 2 N's or is there 4?
3.
4 N's? 1 N. We'll leave it. All right, so we'll go ahead and connect to that guy. So now we see that we created a child, and now we're listening again. Okay? Now, while the person's still deciding what they're typing in, I'll go ahead and connect from another port there. Another child was just created, and now we're listening again. I'll go ahead and I'll finish this one. I'll type in LOL and press enter. He got the hello from server. So that program actually finally ended. The child now is died. This guy's still waiting. Hello. There's him talking. So we're talking to two different versions of the server. Okay. Yeah. Well, no, actually, this guy is he was ending. We just didn't close the socket, so we actually have a little bit of a kind of a poorly written network program right now. We just cut him off. You know, like when somebody hangs up on you, but you're still talking on the phone. Return 0 makes the child end, because return means that this function is over and the function we're in here is main. So the children are dying. We're just not See, I told you, the children they're dead. We got dead kids. All right. So what we do need to do at the very end is we do need to close that socket. I think we should just be able to do that with close new socket, and I think that will do it. Okay, he's listening. We'll connect there. He's listening again. We'll connect there. We'll say LOL there. It's not disconnecting from there. Interesting. We'll do whatever here. So both of those are still hanging on. The server has kept them connected. They'll disconnect here if I do that. Now they're both going to be disconnected. But it was held open. Let me just do C close socket. We might have to flush it. All right, so I can give it the shut that guy. So we'll shut it down, passing it the file descriptor. And we're shutting down new socket. Just 2 commands. Yep, and then I keep wanting to think that's running in my terminal. And that's how. So don't allow any more read writes. Let's see if that works differently. Connected, LOL. He ended nicely now. This guy's still there. Hello, he ended nicely. Server's still listening. We can connect again now. Woot. So on and so forth. All right, so what's the weakness of our current setup here? What's the difference between, we talked about fork at the high level. What's the difference between a fork and a thread? How much detail did we go into about forks? I thought I talked about it a good amount, or did I remind me? Yeah, birds and bees of the instructions. Oh yeah, we talked about it in quite a bit of detail. So what's the difference between fork and thread? We didn't necessarily discuss threads, but why are forks dangerous? They're easy to write, that's why we wrote them. But why are they potentially dangerous? What do you mean by memory? Okay, why?
I'm just trying to compare with threads. And threads will just, the tiny segment of the code will be,
Okay.
But in fork, it will just create the whole.
So fork creates an entire process control block. Creates one of those guys. So it's a whole program. In fact, every single time we make a copy, every single time we fork here, we get a brand new copy of this entire program. All the memory, everything that's been taken, we get a copy of it. Okay, so not only, so we're not just picking up where we left off. If I were to print out right here, after we're the child, if I were to print out some piece of information that we had above here, he would know about it. He got his own copy of that. So if I had 5,000 variables defined up there, I get copies of those 5,000 variables, even though they might be meaningless from this point forward. Okay? So what a fork does is it literally creates a duplicate of the current program. And it continues on from that point forward. But it does mean we get all the scope that was previously defined there. So it continues on from that point forward, which means when we fork right here, the next line that will happen in both of those programs is line 65. And they'll try to decide, who am I? Am I the clone or am I the original? Does that make sense? And they'll continue on from there. So the child went and did this logic, where the parent did this logic. At the end of the child's logic, we kill off the program. At the end of the parent's logic, we spin back up and wait for another incoming connection. Right, so first of all, these guys use a lot more system resources, right? Because they're using memory, they're using, they have a lot more memory. They're using an entire process control block. What about scheduling on the CPU? Yeah, so a process, a full-fledged, true-life process gets full CPU time. So you might say, oh, well, that's good. Let's create 30 processes. Now I get 30 times the CPU time. As long as I can break my problem down into 30 pieces, right? I can just take over the operating system. Instead of getting, 1/30th of it, I get all of it. Or at least I'm going to be on the CPU often. That's kind of the idea. We have decided that context switching is expensive, though. So now we've added a lot more people to the line. So maybe we've hurt the efficiency of our program as well. But one possible issue with this is we can real quickly crash our program. And possibly our operating system. My hope would be, I'm maybe a little afraid to test it, but it might be fun. No, is the current version of Linux that Amazon Web Services is running has some sort of protection about how many processes a user account can create. Because what keeps me from just creating a while loop, an infinite loop, and throwing the fork command in there, and just having, whether you're the child or the parent, you just do it again. you just fork over and over and over again, using up all. I mean, we talked about last time that at least historically, the total number of process IDs was 65,536. It might be more than that now. Maybe it's the 2 billion. Actually, it would be 4 billion because it would unsigned 32-bit number, 4.2 billion. But that's still a lot. I wonder what the maximum number of processes is. Let's just do it. So we're gonna do this right. You know, we're going to really just exaggerate it because it doesn't matter whether you're the parent or you're the child. You're going to create another. So it's just going to be so good. Oh, actually, we don't even need you. Actually, that is true. I do have to consider this is not sued, but this is billable. For all I know, they're charging per process. It'd be pretty funny. It'd be really funny. Here, let me try something here real quick. I think I put it. Right, I actually installed a copy of Ubuntu Linux on VirtualBox. So I'll test it on here. It's a little sluggish. That's why I've been using the Amazon thing, because you can do it. Once I'm in the terminal, we're set. Nailed it. All right. So, huh? No. We'll just keep creating processes and then have each one just have infinite loops in them.
It's gonna be exponential, right?
Yeah.
Because each one will
Yeah, we'll just
speed up more.
yeah, we'll just have it printing out. Oh, that would make it super bad. Because if you're doing prints, then you're just So we'd be creating just zillions of processes, and each process does exactly one thing. It prints a number to the screen, which means that it context switches on and immediately context switches off to get into the I/O queue. But we'll create a whole bunch of those. And we already saw this thing was already slow. Oh, this is going to be exciting. All right, good. So let's do man fork uni std. Wasn't happy about that. Very funny noises. All right, so let's do while one. It's not, it didn't map that that key quite right. Okay, so now we'll go ahead and do int PID is equal to fork if PID is equal to 0, printf LOL \n. Oh, but we're going to do that inside of a while one. right, so that's what that guy does. Just infinite loop just prints out LOL if you're the child. Otherwise, we spin right back up and create another child. All right, so I need to create a second terminal here so we can watch what happens. Give me a new one. Oh my gosh, this is unusable. Not enough, clearly. I'm also doing a screen capture and some of it at the same time. All right, at this point, I just want to get back into this window. I would do it on the local machine here, but I don't want to crash my screen capture. This is taking up too many processes.
I'll try that on mine.
We're there? All right, we're there. All right. So GCC test.c. It looks like it, since I only got 2 hello worlds printed out.
It's supposed to print out a world with all the ones.
Oh, you're right. Test.c was the name of my, yeah. Oh, no, it does. It prints out hello world. Oh, you're right. That isn't what I wrote. What was the file I just edited? Oh, text.c. Oh, yeah. Every single one of them is a brand new process.
Run another terminal with BID. What was the top?
I can't open another terminal. I can't even use the mouse. We already tried that. It was all I could do to get back to this window. Actually, the real slowdown here was that I did printing. So now, effectively, we've done a denial of service attack on our own machine. Because now we've bogged down the process scheduler for the CPU, right? Because now we're constantly context switching on and off. And at the same time, we're also spawning off new children who are doing that same thing. So we got the line keeps getting longer and longer and longer and longer until we'll eventually just run out of processes. Although it is tough to say right now. Yeah. We have to do a little modification here. I'm actually going to say, hey, hey, hey. If it's not equal to 0, if we're the parent, then we're going to go ahead and we're going to print out. I don't even need to print out LOL. We'll just print out different. Oh my gosh. %D. And we'll print out PID. And then we'll let the child actually do the new fork. That way we can tell whether who's printing. If the numbers are changing, we know it's different children because they'll each have different PIDs. So you actually can feel the context switching now. Every single time you see a bunch in a row, oh yeah. So this would be a very bad program to just create that many processes. All right, let's see if I can at least escape out of this. What's my thing to? Guess OS supports mouse pointer integration. What if I want to not have mouse pointer integration? Oh yeah. Is there a way to do that without hitting the mouse? Is there a shortcut? Isn't it like Command Space or something?
Command Q.
Command Q. Woot. Power off the machine. Yes. Okay. So in any case, we've gotten a pretty good look at how fork works, and we've gotten a pretty good look at how the sockets work. So now we want to bring those two pieces together, and for our homework, modify your existing file server to accept an infinite number of incoming. Actually, you know, yeah. Let's. That way you have to use the child numbers. So number of incoming connections, and be able to simultaneously. Man, I screwed that up, didn't I? Nailed it. And be able to simultaneously serve the requested files to them. For right now, you might not be able to test it from a web browser. So you might need to type in something like get index.html, and that would spit out the index.html file. But that's what our thing already does. Now you're just doing it over the socket. Make sense? All right, so homework for Wednesday. No, absolutely not. So this code. So here's your infinite loop code. This is not the infinite loop code, right? Yeah, that's not infinite loop code.
It won't be a class on Friday.
I know.